Alright, so in this video, I'll demo the code for the ML implementation and base code setup necessary for recommending books to users based on skill level or performance or progress. Basically, however you decide to word quantifying score values in books. My original plan was the following. I feel like I should preface this before I go on into my actual implementation. So the plan was to have the backend server running, the application logic and API, have the front end server just basically serve the user interface for the application, um, have a PostgreSQL database, store the application's data, and the MinIO to provide object storage. So I want to make it clear that like all of this still exists in the current implementation because that's the way the code base is set up, and that's the way it functions. But in my previous implementation, I decided to create a separate service that would run the machine learning algorithms to analyze the data from the database. So I would create a new container called ML service and get that running. I also created a Python file called mlservice.py, which would read data from the PostgreSQL database, perform the calculations, and output the results. My ML service would use the PsychoPG2 library to connect to the PostgreSQL database, running in that separate Docker container. It would then run an SQL query fetch, or SQL query to fetch the data from the tables. And from there, I would process that data. But unfortunately, I ran into way too many issues, mostly compatibility problems. And then I recall speaking with Noah, and we basically just changed the game plan entirely. And I scrapped all the work I had initially done because it just was not feasible. And it wasn't the best approach in general. So, as mentioned last time, I prefer reinforcement learning or Q learning for the ML approach. So, before I get into what I've done for my project implementation, I'm gonna briefly explain the ML approach in a simple way, or at least the way I understand it. So, I believe reinforcement learning might be ideal because I'll be able to track specific user progress with that. A machine basically makes decisions by receiving feedback from its actions, right? So it learns from reward slash punishment feedback to find the optimal solution. So ideally, in our reinforcement learning model, we'd need to personalize learning paths for students and adaptively suggest books that fit their progress, right? So the implementation would be categorized into what's known as the agent, the environment, the state, the action, and the reward components. So to get into that, the agent is the algorithm that suggests the books or might perform a calculation related to doing so. The environment is the students and the books themselves, right? The actions are a recommendation of the book, and the reward is the feedback on that action itself, such as like improvement in student performance, right? Or the score, however you want to quantify it. So, if we wanted to implement this specifically, we determine the different states of student learning, like beginner, intermediate, advanced, and the action, like suggesting a book or specific question in a book. Then we establish a reward system. So if a student shows improvement after a suggestion, the agent receives a so-called reward. And to train this agent, we can use user data to simulate various learning paths to decide which actions would lead to the best outcomes, right? And then finally, we would implement the trained reinforcement learning model in the system, and it would essentially adapt in real time. And we're going to get into that later. That's why we're going to use the background tasks. So, as for a specific machine learning algorithm, I think Q learning would work. It seeks to learn the value of taking a specific action in a specific state, and this is known as the Q value, right? It then updates Q values based on the reward that the agent received after taking a specific action. So we would essentially just create a Q table with states showing different learning levels and actions that represent book recommendations. Then we choose an action by trying new books and recommending known effective books. After observing the reward, which is the student performance improvement, we just update the Q value using a formula you can find online or in any research paper related to reinforcement learning and Q learning in general. So the approach I took for the ML algorithm is much simpler than what was just discussed, but it can be built upon to be as complex and as efficient. So the heavy lifting was planning and figuring out how to go about recommending or sorting books based on user scores or performance levels with the given code base. The foundational code is here, right? But with more testing, it shouldn't take much more effort for this to actually run and work. Um, all right, I'll start with an overview of everything, then go into each file and explain them in depth. So this is where the actual code demo begins. So books.py, this handles creation, editing, and searching of books. It also manages book recommendations based on user performance. Next is interactions.py. It manages user interactions with the books, including storing interaction data and actually updating user scores using the Q learning algorithm that was mentioned earlier. Then we have schema.prisma, just a few additions here. It defines the database schema, including models for users, books, interactions, and user scores. And as you can see right here, I have the user book score data table created already. And also, if I open up the actual database, you can see that the schema is present all the way down here. So let's go into books.py and actually talk about the code itself and everything that I've implemented and everything that's already existed and how it all works together. So the search books endpoint is a get endpoint to search for the books. The function parameters accept optional parameters for filtering. The filter conditions involve a where, like dictionary, and adds filters based on provided parameters. So this line right here, books equals await, fetches the book from the database, and we use Prisma and specified filters. It includes related courses, pages, and order by category. And below that, we retrieve the user associated with the provided user token, right? And that was the issue that Noah solved after him and I were on a call for like 4 hours. I believe no API key was being sent when a user was logged into the website while on the home page. So that kind of prevented everything from working properly. So that was a bit of a roadblock. Next is user scores. To fetch the user scores, I initialized an empty dictionary for user scores, and if a user is logged in, it fetches the user's book scores from the user book score table that we created earlier. So to store scores, it creates a dictionary mapping. It creates a dictionary mapping and it maps book ID to score. Um, and this if statement right here. So this is basically a query-based book filtering that already existed, but I had to just edit slightly. Essentially, if a query is provided, it filters and sorts books based on query match count and my implemented user scores as well. So it uses regular expressions to find matches in book details and sorts books by match count and user scores in descending order. Descending order specifically because that way students who perform poorly on certain books are recommended said books first within the query match results, right? You don't want to recommend a book that a student did really well on over a book that they did poorly on because you want them to do better and improve before moving on, right? Also, from the else statement right here, you can see that if no query is provided, books are sorted by user scores in descending order automatically. So I basically had to learn about multiple keys in Python in order to do this originally. Um, and then the rest of the code is just what's already been there. Like get book is an endpoint to get details of the book by its ID, and it fetches the book from the database, including related pages, then raises a 404 error if book isn't found, right? There are also other post and put endpoints as well down here that I don't really need to get into. They all have authorization checks to make sure that only like a teacher is able to perform those actions, right? So that was books.py. Moving on, we can go to interactions.py. So it has fast API libraries for creating endpoints and background tasks, which we'll get into shortly, and why they're important for this ML implementation. So this code already existed here, but I'll explain because it might be necessary for the rest of it. So interaction create request is used for the data models. It defines the data structure for creating a new interaction. This includes details about like the interaction type, time taken, user ID, question ID, etc. Interaction create response defines the expected structure for the response after creating an interaction containing just the interaction ID. Okay, so now on to the more important stuff, Q-learning and Q-table initialization. So here you can see alpha is the learning. It controls how much new information overrides the old information. And gamma is the discount factor, so it measures the importance of future rewards, basically. And epsilon is the exploration rate. So it controls the trade offs between exploration, so trying new things, and exploitation, so using known information. And here you can see Q. Q is basically the Q table. It's a dictionary for storing Q values for state action pairs. Um, Next, we have state and action function. So you can see here, get state extracts the state from the interaction data. The state is it's represented as a tuple of like user ID, book ID, and page ID. And then we have get action. Get action chooses an action based on the epsilon greedy strategy. So with probability epsilon, it chooses to explore, meaning try a new action, right? Otherwise, it will exploit, meaning it'll choose the best known action. So that's how that works. And here's the QTable update function. It updates the Q value for the given state action pair using the Q learning update rule. It initializes Q values for state action pairs if they don't already exist. It also calculates the maximum future Q value and updates the current Q value based on the reward received and the future Q value itself as well. So yeah. Next, we have the score calculation function, which is pretty basic. It just calculates the score for an interaction using the Q learning algorithm. It retrieves the current state and decides on an action. It also determines the reward based on the correctness of the interaction. It updates the Q table with the current state, action, reward, and the next state. Then it also returns the calculated reward as the score. So if the user gets the question correct, the reward is 10 points added. Otherwise, it's 5 points subtracted. So yeah, that's that function. Okay, now we have the run ML inference function. It runs the Q-learning based inference to update user scores. Then it checks if a score is already existing for that user book pair. This basically acts like a database update, right? So if it does exist, it updates the existing score by adding the new score. If it doesn't exist, it creates a new score record in the database. So yeah. And here's the interaction creation endpoint, most of which already existed. It only needed like 2 lines in order to run the background ML inference. So basically, this defines a post endpoint to create a new interaction. It creates a new interaction record within the database, and then we add the run ML inference function to the background tasks to handle calculations and database updates asynchronously, right? We don't have to do anything manually, so that's the reason we need those background tasks. This endpoint is basically this endpoint is really important because it's intended to create interactions which are processed to update user scores and inform future book recommendations, right? So our Q learning algorithm, it's intended to use the state, which is the user ID, book ID, page ID, and the action, so explore, exploit, right? To technically learn and improve the recommendation system over a long period of time. So yeah, that's that. I also forgot to mention that if you're going to be working locally, make sure the openapi.ts URL is set to your database for front end. So as you can see here, mine is set to localhost 8080. That's important, so don't forget that. Lastly, what else do I have to say? Oh yeah. So I had written test files for books.py and interaction.py. All the tests passed. The only problem was that they're not updated. So they passed before I replaced the basic calculate score placeholder function with the Q-learning algorithm itself. So with that in mind, the next steps I suggest that you take, or whoever takes on this project, are to ensure score tracking for all attempts, right? So for state representation, ensure that the state includes like sufficient information to track different attempts. For reward calculation, ensure the reward system appropriately like reflects both correct and incorrect attempts. And for interaction logging, each interaction should be checked as properly logged in the interaction table, including whether it was correct or not, right? And then also track all interactions and make sure that interactions are storing all question attempts, including incorrect and correct answers. The reason I mention this and reiterate this is because books function in a way in which the user cannot move on to the next question or complete a book until they've gotten the current question that they're on correct, right? So you can't move to the next question until you've gotten it correct. If any questions that were like attempted and answered incorrectly are being overridden within the or yeah, if they're being overridden right with the mandatory correct answer before being allowed to move on, and nothing is being tracked or stored, then we should account for this by either adjusting the current approach or adding more functionality to the data tables themselves, right? Um, I hope that made sense. It was a bit all over the place. So yeah, I guess the concrete next steps to take are to verify the interaction table in the database and ensure it logs every attempt with the proper correct fields or field values, and that no interactions are being overwritten at all. So just write test cases to make sure that all interactions are logged appropriately. Um, in theory, right, following these steps that I just mentioned would only require small adjustments to the current code and ultimately lead to a working ML implementation. The base code of all of this is here, right? All you have to do is build upon that, and you should be set. So yeah, that's about it.